Welcome to the deep dive. Today, we're going deep, really deep into Euclid's Elements, the book that basically built geometry.
Oh yeah, Elements, it's a classic.
It is. We've got excerpts from a book all about it, and we're going to unlock its secrets.
Awesome. By the time we're done with this deep dive, you'll know all about the historical context.
Yeah, Euclid's impact.
And some of the big ideas that still matter today. It's amazing how this one book, written centuries ago, is still so relevant.
I know, right? And speaking of history, our mysterious author, Euclid, we know almost nothing about him.
True. Very little info out there, but his work speaks for itself. Elements brought together like centuries of Greek mathematical thought.
Yeah. It presented it all in a structured, logical way, and that approach is what makes it so influential. It's not just about shapes and angles.
It's about the power of thinking logically, step by step.
Right, like that story about King Ptolemaeus.
Oh, I love that story.
He wanted a shortcut to learning geometry.
He was like, is there an easier way, Euclid?
And Euclid, in his classic no-nonsense style, just said, there is no royal road to geometry.
Oh man, he was so blunt.
It shows how much rigor, how much dedication it took to master this field.
No shortcuts.
None. So let's talk about the steps, the building blocks. The book starts with definitions, postulates, and common notions.
It's like setting the stage, laying the foundation.
Exactly.
You've got definitions trying to describe those basic geometric concepts we all kind of know. You know, like points, lines, circles.
Okay, and the postulates are like the rules specific to geometry.
Right, like a straight line can be drawn between any 2 points.
Got it. Makes sense. But what about these common notions?
Oh, those are more general assumptions. Like in math, things we just accept as true.
Yeah.
Things equal to the same thing or equal to each other. Stuff like that.
Yeah. Okay, that makes sense. But the source mentions that some of Euclid's definitions are kind of circular. They rely on terms he doesn't actually define.
That is so interesting.
Doesn't that, undermine the system?
Well, it's a good point. Think about the definition of a point. He says it has no part.
But what's a part?
Exactly. Not really defined.
It's like one of those optical illusions. What's figure and what's ground?
Totally.
It makes you think.
Right.
Are these math objects real or just ideas in our heads?
Big philosophical question.
We're going deep.
We are.
Okay, but let's get back to the postulates. Which one was the most controversial?
Oh, definitely the parallel postulate. It's famous, and for good reason. It says, through a point not on a line, you can draw exactly one line parallel to the original line.
Okay, but they couldn't prove it.
Nope, not using Euclid's other postulates and common notions.
Wow. So this basic rule wasn't provable within the system.
Right, and it bugged mathematicians for centuries. It was a major, major sticking point.
I bet. And then...
And then came guys like Lobachevsky.
Okay, what did he do?
He said, what if we tweak this postulate? And guess what?
What?
Boom. New geometries. Non-Euclidean geometries like hyperbolic geometry.
Whoa. Hold on. Are you saying there are different kinds of geometry where the rules are totally different?
Yes.
Mind blown.
Right.
So, Euclidean geometry, the stuff we learn in school, works on flat surfaces.
Yeah.
But what if the surface is curved?
Like a sphere.
Like a sphere.
Exactly.
The rules would have to change.
They do.
So, in hyperbolic geometry, there can be infinitely many parallel lines through a point.
Yes. Think of it like...
It's like discovering a parallel universe where up is down.
Exactly. It's a whole new set of rules. And it all started with this one assumption, this one postulate.
Incredible. So Euclid's ideas about space were groundbreaking, but what about something as huge as infinity? How did he approach that?
Well, we got to think about the philosophy of the time. Aristotle, he was a big influence, believed in potential infinity.
Potential infinity?
Meaning things can go on forever, but you never actually reach infinity itself.
So, you can always add one more, but you never get to the final number.
Exactly. And this idea had a massive impact on Euclid. He avoided dealing with infinity directly.
Interesting. But he still had to deal with stuff like parallel lines, right?
You got it. And those, by definition, go on forever.
So he was kind of stuck between a rock and a hard place.
Right. He couldn't completely avoid it, but his approach reflects the philosophical limits of his time.
Fascinating. It's like he's doing this balancing act between math and philosophy.
Totally.
Speaking of balancing acts, let's talk problem solving. I love that the source mentions tangrams.
Tangrams.
Those fun little puzzles.
They are.
But they're also deeply connected to geometry.
Right. It's visual problem solving.
Exactly. You can see those geometric relationships without needing complex equations.
And that's kind of what Euclid did with his proofs. He had these tangram-like methods, like his famous proof of the Pythagorean theorem. He's dissecting squares and triangles, showing how the areas relate.
Like a visual proof. Did he use this method for other things, too?
Oh, yeah. Algebraic identities. The concept of quadrature.
Quadrature.
Constructing a square with the same area as another shape. He mainly focused on polygons for that.
It's so creative.
It is.
Euclid, the artist. Okay, are you ready for the golden ratio? This one's a big one.
Let's do it. It pops up everywhere. Art, architecture, nature. It's amazing how this mathematical concept can have such far-reaching implications.
So, remind me, what is the golden ratio?
It's a relationship, a
Mhm.
proportion. The larger part of a segment is to the smaller part as the whole segment is to the larger part. And it's represented by the Greek letter phi.
Phi, okay. But people say it's related to beauty, right? Like it's found in the human body and all that.
Yeah, there's that whole thing about it being a hidden code of nature, but Euclid, he was focused on its mathematical properties, on how to use it in geometry. Like, he used it to construct a pentagon.
The pentagon, cool. Any other shapes?
Oh yeah, he described how to construct a golden rectangle.
A golden rectangle. Okay, what's special about that?
It has this crazy self-replicating property. You can cut a square off, and the leftover part is another golden rectangle. And you can do that forever.
Whoa, it's like a fractal.
It is, kind of.
It's hidden in this simple rectangle. Okay, that's 2 dimensions, but did Euclid venture into 3 dimensions?
He did.
I vaguely remember something about platonic solids from school. They always seem so.
Mysterious.
Yeah, mysterious.
Well, they are pretty amazing. 3-dimensional shapes made up of regular polygons. And Euclid devoted a whole book of elements to figuring out how to construct them.
There were 5 of them, right?
Yep, you got it. The tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron.
I can barely pronounce them, let alone construct them. How did Euclid even figure out how to do that?
He used this really clever combination of analysis and synthesis. Like with the tetrahedron, he imagined it already existed and then figured out its properties.
Like reverse engineering.
Totally.
Yeah.
And then he used that knowledge to work backward and develop the steps to construct it.
Brilliant. It's amazing. Did anyone else build on his work with the platonic solids?
Oh yeah. Centuries later, Luca Pacioli, an Italian mathematician, connected them to the golden ratio. He was all about finding those hidden links.
So even centuries later, people were still finding new connections and insights in Euclid's work. It's incredible.
It is. Now, are you ready to tackle a problem that stumped mathematicians for a really long time?
Bring it on. What is it?
It's the problem of incommensurable magnitudes.
Okay, break it down for me. Incommensurable magnitudes. What are we talking about?
Imagine you're trying to measure 2 things, but can't find a unit that fits perfectly into both. Like, it's impossible to find a common measure.
Oh, I see. Like trying to measure the length of a table and the height of a bookshelf with the same ruler, and it just doesn't work.
Exactly.
But how did they even figure out that this was a thing?
Well, it probably came from discovering irrational numbers, like the square root of 2.
Yeah, those always messed with people's heads. Especially the Pythagoreans, who were all about those nice whole numbers.
Totally. It was like finding a crack in their perfect mathematical world.
So how did Euclid handle this?
He used the brilliant work of Eudoxus, who developed this whole theory of proportion just to deal with these tricky cases.
So instead of trying to find a common measure?
You look at how many times each magnitude fits into a larger one. It's like shifting your perspective.
Ah, I get it. So what did Euclid accomplish with this new tool?
Well, it helped him figure out areas and volumes of curved figures.
Oh, how is that even possible? We usually need calculus for that kind of thing.
I know, right? But the Greeks had this technique called the method of exhaustion.
Method of exhaustion. Sounds tiring.
It kind of was. Imagine you're trying to find the area of a circle.
Okay.
You start by drawing a polygon inside, like a square. Then you add more and more sides to the polygon.
Making it look more and more like the circle.
Yep. And Euclid used this method to prove the relationship between a circle's area and its diameter, something we still use today.
It's amazing what they could do without modern math tools. But wasn't it Archimedes who really went crazy with the method of exhaustion?
You're right. He took it to a whole new level.
He was a total genius.
He was. Okay, ready for another brain teaser.
Hit me with it.
Squaring the circle.
Oh yeah, that one. Construct a square with the same area as a circle using only a compass and a straight edge. Sounds simple enough.
Right, but it's not. People tried for centuries, and guess what?
It's impossible.
It's impossible.
Proven.
All those mathematicians.
Wasting their time.
But hey, even if you fail,
you can still learn a lot along the way.
Exactly. It's like getting lost but finding something unexpected and amazing.
Yeah.
Speaking of journeys, what about the journey of elements itself? How did it make it through all these centuries and shape the world?
It's an amazing story of survival and influence. Think about it. From ancient Greece to the Roman Empire.
To the Islamic Golden Age.
Exactly. Islamic scholars recognized how important Euclid's work was. They translated elements into Arabic.
They were keeping the knowledge alive. They were. And they didn't just copy it. They added their own interpretations and commentaries.
Wow, that's cool. It's like this cross-cultural dialogue about math.
It is. And then, as Europe started to come out of the Middle Ages,
They rediscovered the classics.
they did. Elements got translated into Latin from Arabic and became a major text in universities.
So it like went on this world tour and then came back home.
Exactly. And it influenced everyone. Leonardo da Vinci, Johannes Kepler, Isaac Newton, all these brilliant minds were studying Euclid.
Wow, that's incredible. What's the secret to its lasting power? Why has it resonated for so long?
Well, Euclid was really good at explaining things. Clear, concise, and logical. He took complex stuff and made it understandable.
Yeah, you can really see that in Elements. But I think it's more than just good writing.
Right.
It speaks to this deep human need to understand the world, to find those underlying patterns.
Absolutely. It's like a blueprint for logical thinking. And that's why its influence goes way beyond math, philosophy, law, even computer science.
Yeah.
They've all been shaped by Euclid's way of thinking.
Okay, before we move on to part 2, I think we need to talk about Euclid's work with numbers.
Oh, yeah, the arithmetic. It's easy to forget about that with all the geometry.
Yeah, I know, but it's just as important. So where do we begin?
Let's start with prime numbers, those building blocks of the number world.
Ah, prime numbers, the numbers greater than 1 that are only divisible by 1 and themselves. I remember those. Did Euclid make any headway with them?
Oh, he did some amazing stuff. He proved there's an infinite number of prime numbers.
Wow.
And he came up with a method for finding the greatest common divisor of two numbers. It's called Euclid's algorithm.
That's still used today, right?
Yep, it's a classic.
Euclid was ahead of his time.
He was. Okay, now let's talk about perfect numbers.
Perfect numbers, what are those?
A perfect number is a number that equals the sum of its divisors, excluding itself, like 6. Its divisors are 1, 2, and 3, and those add up to 6.
But like the number is in perfect balance.
Exactly. And Euclid, he didn't stop there. He figured out a way to generate perfect numbers using, you guessed it, prime numbers.
Those primes again.
They're everywhere.
Yeah.
He showed that if you have a prime number of a very specific form, 2 to the power of n minus 1, where n is also a prime number, well then you can create a perfect number.
Okay, I'm going to need a minute to process that one. But it just shows how deeply Euclid understood the connections between numbers.
He did. And those connections are still being explored today.
That's amazing.
Now for another classic problem, squaring the circle.
Ah, yes. Using only a compass and a straight edge, construct a square with the same area as a circle.
Sounds simple, right? But mathematicians tried for centuries.
And?
It's impossible.
No way!
It's true. It was eventually proven.
All those brilliant minds on a wild goose chase.
But you know what? Even those failures can lead to new discoveries. Sometimes you have to get a little lost to find something truly amazing. Speaking of journeys, what about the journey of elements itself? How did it survive for so long?
Yeah, how did it influence the world?
It's a story about the power of ideas, from ancient Greece to the Roman Empire.
To the Islamic Golden Age.
Exactly. Islamic scholars translated elements into Arabic.
Wow, they really saw its value.
They did. And they didn't just copy it, they added their own ideas and interpretations.
It's like this cross-cultural conversation about math.
It is. And then, after the Middle Ages, Europe rediscovered the classics.
And Elements made a comeback.
Big time. It was translated from Arabic into Latin and became a core text in universities.
Wow, so Elements went on this world tour and came back more influential than ever.
Exactly.
It's incredible. Why has it had such a lasting impact?
Well, Euclid was a master explainer. His writing is so clear, concise, logical.
Yeah, he really breaks down those complex ideas, but I think it's more than that. It's like he tapped into something fundamental about how we think, about our desire to understand the world.
I agree. And that's why Elements has influenced so much more than just math. We see its fingerprints in philosophy and law, even in computer science.
It's really amazing to think about. Now, before we move on to part 2, I want to touch on something we talked about earlier. Non-Euclidean geometries.
Oh yeah, the geometries that break the rules.
Right. Those were the ones that challenge Euclid's assumptions about space and geometry.
And they're not just theoretical curiosities. They have real implications for understanding, like the universe.
Okay, I need a refresher. How do these non-Euclidean geometries differ from the geometry we learn in school?
Well, one big difference is in the idea of parallel lines. Remember, in Euclidean geometry, through a point not on a line, there's only one line parallel to the original.
Right, that's what I learned.
But in non-Euclidean geometry, it's a different story. Sometimes you can have an infinite number of parallel lines through a point, and sometimes, get ready for this,
What?
parallel lines can actually intersect.
Whoa, that just sounds wrong.
And I know, it bends your brain a little.
But how can that apply to the real world?
Well, it turns out our universe, on a really grand scale, doesn't quite follow those neat Euclidean rules. Einstein's theory of general relativity, all about gravity warping space-time, well, that needs non-Euclidean geometry to describe it accurately.
So Euclidean geometry is fine for our everyday world.
For building bridges and houses, yeah.
But when we're talking about the universe, black holes.
We need something more powerful.
That's amazing. So even those unchangeable truths of geometry, they can be challenged. It makes you wonder what other mind-blowing mathematical discoveries are out there, just waiting to be found.
It's exciting to think about, right? We've only just begun to explore these new geometries, these new possibilities. It's a whole new frontier of mathematics. Welcome back to our deep dive into Euclid's Elements. We've covered a lot of ground, but there's still so much to uncover.
I know, right? It's amazing how much there is to unpack in this book. Last time, we left off talking about Euclid's work with numbers, particularly those fascinating Pythagorean triples.
Oh yeah, those are a great example of how Elements brings together geometry and arithmetic. But before we get back to the numerical stuff, let's talk about the journey of this book itself.
A historical journey.
Yep, it's a story of survival and influence, like from ancient Greece to the Roman Empire and then on to the Islamic Golden Age.
Oh, wow. So even when Europe was in the Middle Ages, the knowledge of elements was still being passed down.
Exactly. Islamic scholars, they really understood how important Euclid's work was, and they saw its value for advancing their own mathematical knowledge. And they weren't just copying it.
They were, what, adding their own thoughts?
Yeah, they were engaging with it,
Yeah.
adding their own commentaries and interpretations.
That's amazing. So it was like a conversation across different cultures and centuries.
I like that, a conversation about math. And then, as Europe began to emerge from the Middle Ages, there was this renewed interest in the classics.
They rediscovered those ancient Greek texts.
They did.
Yeah.
And Elements was translated from Arabic into Latin,
Yeah.
making it available to European scholars. And then it was like, boom, a revival of interest in geometry.
It's like Elements went on this incredible journey, gathering wisdom from all these different cultures, and then it returned to Europe, and it was like a hero's welcome.
Exactly, a hero's welcome. Elements became a cornerstone of university education. I mean, think about it. Leonardo da Vinci, Johannes Kepler, Isaac Newton, they all studied Euclid.
That's mind-blowing. What do you think is the secret to the book's success? Why has it resonated with so many people for so long?
Well, Euclid's writing, it's just so clear, so logical. He takes these complex ideas and breaks them down, step by step. But I think it goes even deeper than that.
Yeah, I agree.
It's like he taps into this deep human need to understand the world, to find the patterns that underlie everything.
It's like a guide to thinking clearly and systematically.
Exactly. It's like a blueprint for reasoning. And that's why its influence goes beyond mathematics. Philosophy, law, computer science, they all owe a debt to Euclid.
Okay, let's loop back to those Pythagorean triples. I'm still fascinated by them.
Oh, yeah. Those sets of three whole numbers that fit perfectly into the Pythagorean theorem. Remember, Euclid didn't just describe them. He figured out a way to generate them.
Right. With just simple arithmetic, he could create these triples. Okay, remind me how that works.
It's pretty neat. You pick any two whole numbers, right? Let's call them m and n, where m is bigger than n. Then you apply these three formulas. The first number is m squared minus d squared. The second number is 2 times m times n. And the third number, which is the hypotenuse, is m squared plus n squared.
Let me see if I remember. Okay, if I pick 5 for m and 3 for n, all right, so I get 16 for the first number, 30 for the second, and 34 for the hypotenuse. Did I do it right?
You got it. 16, 30, and 34, that's a Pythagorean triple. It's such a simple, elegant method.
It really is. Euclid just had this amazing ability to take something that seemed complex and make it so understandable.
He did. Now let's talk about perfect numbers.
Perfect numbers. I'm not sure I'm familiar with
A
those.
perfect number is a number that equals the sum of its divisors, but not including the number itself, like 6. Its divisors are 1, 2, and 3, and when you add those up, you get 6.
It's like the number is in perfect harmony with its parts.
I love that. It's in perfect balance. And Euclid, he didn't just observe this. He figured out a way to generate perfect numbers.
Really? How did he do that?
He used prime numbers.
Prime numbers seem to be everywhere.
They are. They're kind of the DNA of the number world. What Euclid showed was that if you have a prime number with a specific form, 2 to the power of n minus 1, where n is also prime,
Right.
you can create a perfect number.
Okay, I'm going to need a minute to process that one. It's amazing how he found those connections.
He was a genius.
Yeah.
And those connections are still being studied by mathematicians today. But let's move on to another classic puzzle that stumped people for centuries. Squaring the circle.
Oh, right. You have a circle, and you're trying to construct a square with the same area using only a compass and a straight edge.
Yep, sounds easy enough. But
Yeah.
guess what?
It's impossible.
It is. It was proven to be impossible.
Wow. All those mathematicians, all those years of trying,
Yeah.
and it was all for nothing.
But, sometimes you have to explore those dead ends to make real progress.
Yeah, sometimes getting lost leads to unexpected discoveries.
Exactly. And speaking of journeys, let's talk about the incredible journey of elements itself. How did it survive all those centuries and become so influential?
Okay, take me back to the beginning.
It all starts in ancient Greece, where Euclid wrote Elements. But its influence spread quickly. It was translated into Arabic by Islamic scholars during the Golden Age of Islam.
So they saw its value even when Europe was in the Dark Ages.
Absolutely. They saw how important Euclid's work was. They weren't just preserving it. They were adding their own ideas, their own interpretations. It was this amazing collaboration across cultures.
Wow, that's really cool.
And then, as Europe started to emerge from the Middle Ages, there was this big revival of interest in classical learning, including Greek math.
So Elements finally returned to Europe.
It did. It was translated from Arabic into Latin and became a core text in universities. People like Leonardo da Vinci, Johannes Kepler, and Isaac Newton, they were all influenced by Euclid.
It's incredible to think about how this one book had such a huge impact. What do you think made it so special, so influential?
Well, part of it is just how clearly Euclid explained everything. It's concise, it's logical, it's well-structured. But I think there's a deeper reason, too.
I think so, too.
It's like Euclid tapped into something fundamental about how we think. That desire to understand the world, to find patterns, to figure things out logically.
It's like a guidebook for thinking rationally.
It is. And that's why it's influenced so many different fields, not just math. We see it in philosophy, in law, even in computer science.
It's really incredible to think about how far-reaching Euclid's influence has been.
It is. Now, before we move on, I think we need to acknowledge that Elements, while groundbreaking, wasn't the final word on geometry.
Right, we talked about non-Euclidean geometries, the ones that challenge some of Euclid's assumptions.
And those weren't just theoretical. They had real implications for how we understand the universe.
Okay, I need a refresher. What were those key differences again?
Well, one of the biggest differences was the idea of parallel lines. In Euclidean geometry, remember, there's only one line that can be drawn parallel to another through a point not on the line.
Right.
But in some non-Euclidean geometries, you can have, like, an infinite number of parallel lines through that point. And in other non-Euclidean geometries, get this, parallel lines can actually intersect.
Whoa, that just sounds wrong. How can parallel lines possibly intersect?
It does seem strange, right? But it turns out that our universe, on a cosmic scale, doesn't quite follow those neat Euclidean rules.
So what does it follow?
Einstein's theory of general relativity, the one about gravity as a curvature of space-time, needs non-Euclidean geometry to describe it.
So, Euclidean geometry is fine for our everyday world, for building things, for navigating.
Yeah.
But when we start talking about black holes in the expanding universe,
You need something more.
that's incredible. So even those seemingly absolute truths of geometry can be challenged and expanded upon.
They can. And who knows what other mind-blowing mathematical discoveries await us in the future.
Welcome back for the final part of our deep dive into Euclid's Elements. It's amazing how much we're still learning from a book written over 2,000 years ago.
I know, right? It just shows how powerful and timeless Euclid's ideas are. We've talked about the history, the impact, but now I want to look at how Elements is still shaping our world today.
Okay, let's do it. What are some of those modern day applications? I mean, we all know it's fundamental to geometry, but does it go beyond that?
Oh, absolutely. Euclid's fingerprints are everywhere. Architecture, computer science, art, you name it.
Whoa, okay. I'm intrigued. Let's start with architecture. How did Euclid influence the buildings we see all around us?
Well, think about the core of geometry. Symmetry, proportion, angles, these are all essential for good architecture, right?
Right.
And Euclid's work gave people a way to really understand these concepts. You can see it in so many amazing buildings throughout history. Ancient Greek temples, Renaissance cathedrals.
So they were like putting Euclid's ideas into stone and mortar.
Exactly. They were using geometry to create beautiful, functional spaces. And it's still happening today. Modern architects are still inspired by Euclidean geometry.
So even skyscrapers, they have a bit of Euclid in them.
They do. Okay, now let's jump to computer science. How does a guy who lived before computers even existed play a role in our digital world?
Yeah, that's a good question.
Well, think about computer graphics, CGI in movies, video games, 3D modeling. All of that relies on Euclidean geometry.
No way. Really?
Oh yeah, all those shapes on our screens, they need math to work.
I guess that makes sense.
And it's not just visuals. Robotics, artificial intelligence, all that stuff often uses Euclidean geometry to model the world.
So it's like those robots have a little bit of Euclid in their programming.
Exactly. Okay, ready for a curveball.
Hit me.
Art.
Art? You mean like paintings and sculptures?
Yep. Artists have always been drawn to the beauty of geometry. Think about perspective in Renaissance art, or the intricate patterns in Islamic art. It's all connected.
Wow, I never thought about it that way. So they were using those ideas to make their art more harmonious, more balanced.
Exactly. And that connection is still alive today. A lot of contemporary artists explore geometry in their work.
It's incredible to think about how Euclid's ideas have influenced so many different things.
I know. Okay, one last thing I want to touch on before we wrap up. We talked about non-Euclidean geometries earlier, remember?
Yeah, the ones that bend the rules.
Right. They challenge Euclid's basic assumptions about space.
And those aren't just some weird mathematical theory.
Nope. They actually help us understand the universe.
I need a quick refresher. How are they different from the geometry we learned in school?
Okay, so in Euclidean geometry, there's only one line parallel to another line through a point, not on that line, right?
Yeah.
But in some non-Euclidean geometries, you can have like an infinite number of parallel lines through that same point.
Whoa.
And sometimes in those weird geometries, parallel lines can even intersect.
That just seems wrong.
I know. But it turns out that the universe, especially on those massive scales, doesn't always play by Euclid's rules.
So Euclidean geometry is fine for Earth.
Yeah, for most things here.
But if we want to understand black holes, the universe expanding,
We need something more.
that's so cool.
It is. So even those seemingly rock-solid truths about geometry, they can be challenged. And it makes you wonder what other amazing math is out there waiting to be discovered.
Well, I think we've covered a lot of ground in our deep dive into Euclid's elements. We've explored its history, its impact on so many different fields, and even its connections to the vastness of the universe. It's been quite a journey.
It really has. From ancient Greece to the modern world, Euclid's ideas are still shaping how we think and understand the world.
So keep those minds sharp. Keep exploring. Who knows what geometric wonders you might uncover.
Thanks for joining us for this deep dive into Euclid's elements. We hope you enjoyed the journey as much as we did.